Find the standard deviation of the sampling distribution of p hat. The sampling distribution of p hat. Now this one, you probably won't like, because even though we have p hat, we also have that, don't we? So if I want to find that standard deviation of p hats, I'm still going to use the parameter. 0.40 times 0.60 divided by 1785. And that should produce for you these
0.0115. So why do you need the standard deviation?
What?
Why do you need the standard deviation? Oh, because you need the mean of that?
Right, because if you're going to do a z-score type thing, it's a statistic, parameter, standard deviation of statistics.
Why did you multiply by 0.6 though?
Because it's root PQ over N. That's the formula.
Oh, the other.
The formula is root PQ over N. Oh, where'd my marker go?
Oh,
Yes. You lost it.
You lost me, you lost me.
me every day.
What number was this? 36? Oh, that's all the odds. Okay, cool. Alright?
Wait, but Munoz, so do you like, are you supposed to, here's what happens.
Okay. Part C.
Will you walk me through this one?
Look. Well,
No, it's
they want this. They want the standard deviation of the sampling distribution, right? The formula is P times Q divided by N.
Alright, so what's P, what's Q, what's N?
What's P?
Okay.
He's a success.
So
So P is
0.40,
Oh, success, and then the failure is 0.6 because it has to equal 1.
correct.
Divided by N, what is N?
Sample size.
1785, that's freaking easy, bro.
And then you do it. That's it. Okay.
It's not that easy.
Part C.
Why you gotta make it sound uncomplicated?
I didn't.
Yes, you did.
That's literally what it said. That's literally how you read it.
Didn't he say it all complicated?
No, that's exactly how you said it last time.
Nope.
Thank you. Luis. Focus on you.
Alright, show me which one.
Wooden had a question. What's up, Wooden?
I wondered, like, why on this, the formula sheet, that it has that equation, but it has,
It's 1 minus P.
the 1 minus P
Okay.
equaling that.
Guys, on your formula sheets. Yeah, exactly. You're gonna get. Let's see, what is that? It reads like this: P times 1 minus P over N. And I keep writing PQ over N.
You said 1 minus P is Q.
Okay? So, P is P, right? That's success. Now, if I take 1 and I subtract from that success, what do I get? I get failure. We call failure Q. So instead of writing all this 1,000 times, I just call it Q. Answer your question?
Yeah.
Awesome. Thank you for asking.
See, I remember you saying that.
Good.
I was paying attention.
How do we check to see if it's within the 10%?
So that's what we're going to do next, right? Oh, it says check to see if the 10% condition is met. Well,
Independence, right?
right. Well, this is the 10%. This is independence, yes. Is that what you said? Good. So to check for independence, I have to make sure that the population is greater than or equal to 10 times the sample size. So take that 17, what was it? 1785? If you multiply by 10, you're going to get 17,850, correct? Do you think that there are more than 17,850 U.S. adults that go to church?
Yes.
There it is. As long as that conclusion is reasonable, then you would be like, yeah. Okay. Okay? Cool beans.
What's ion?
Yeah, so like for example, did I say the unicorn example?
Oh, yeah.
Okay, dude, turns out that I got I found 2 unicorns.
N is greater than or
Okay, and I measured their horn because I want to see the average length of the unicorn horn. And then I want to check to see if there was independence. I found 2 of them. Do you think there's really more than 20 unicorns out there? I don't even know how you found the first two, but okay. You see, you get the idea though.
Yeah.
As long as that.
Sorry.
That was you, definitely you.
41. Sorry.
What's up, Katie?
41.
Let me finish 36, okay?
Dang, hurry.
Well, I'm trying. But there's some people having conversations. I didn't say no names. Yourself and Savannah.
I'm just waiting for 40.
I know you were. I just had to do it though. Because I know it was for Carter. Shut up, Luis.
Where's he at?
He's in the back and I can still hear him over here with his Adiana voice. C. Part C says.
So, bro. Part C says what?
Did we?
Yeah, we did part C.
Oh, cool. Then let's do D.
Wait, Part C is the 10?
No, we haven't.
Yeah, that's what that was.
No, that's independence.
Yeah, we just did.
This is asking for normality.
Oh, normality is independent.
Okay, so normality.
So is this C or then, right?
So normality,
That's the sample.
that means that we're looking for at least 10 successes and 10 failures.
Yeah.
So if I take 1785 multiplied by 0.40, is that number greater than or equal to 10?
Yes.
Sure is, right? And if I take that 1785 and multiply by 0.6, is that greater than 10? Definitely. Yeah, of course you want the math, but then you'd be saying, yes, both conditions are met. All right? And then the last one, blah, 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 blah. Do we need to do the last one? Do we need to do D? Who asked me for this?
Oh, yeah.
You did.
I did.
We need to see part D?
I didn't
Yeah.
remember how to do it.
Find the probability of obtaining a sample of 1,785 adults in which 44% or more say that they attend. So they actually want to find out the probability of getting these results we just got. So that means that I'm going to need a z-score. And to get that, I need a statistic. Can someone check it? Is it stat? Minus a parameter? Over the standard deviation of that parameter? Okay. So what's my stat in this case?
What's your what? 0.4.
It's proportions, right? So I need to go p hat minus p over root pq over n.
Okay.
That's going to be my statistic, or my z-score in this case, okay? So, wait, what? Because we want to find the probability. Didn't they ask us for that? For the probability of so-and-so?
Yeah.
So, let's do that. So, what's my p hat?
0.4.
And I believe we already got a standard deviation. Does somebody else have it? Louise, you have it written down?
That's
0.0115.
0.0115.
5.
Sweet. So, what's my z-score?
0.04.
No, the other one. There's another one.
So 0.4 divided by
No,
0.0.
0.04.
Oh, thank you. You're right. Divided by 0.0115. 3.47. I got 3.4. Can someone double check that? Please? That's what I got for a Z-score. I just want someone to double check it. What'd you get?
I got like negative 30.
Oh, you put it all together, so that doesn't work.
I got like negative 34.
You put it all together, it doesn't work. You have to make, because here's what you're doing. You're writing it all in one sentence. It's taking this number divided by this number, and that's going 44 minus that quantity. You have to make sure you put these together in parentheses, and then you can divide it by
Yeah, you're right.
for shout.
So 3.47.
No, that's the Z-score.
Oh.
So what I do with the Z-score?
Just you look at the table.
Take it to the table. So if I take it to the table, and I'm looking for the probability of having a Z-score of that or higher,
It's a 0.99.
it's off the wall already.
Yeah.
I mean, that's the probability of getting stuff that big is very small of what I got. So did I do it right? No. The probability probability of that happening is less than 1%. It's ridiculous.
Wait.
Because that's what we got based on the stats. So if you're off by that much, it's wrong. Okay?
Wait.
Yeah, so go to 3.8. Well, in this case, it's 3.4, right?
Yeah.
So if I go all the way up to 7, that's right here.
I want to make sure I was there.
Yeah, it's still very, very small.
So that's saying that.
All right, cool. Katie, you had which one? 41?
They don't always give you the PM.
On-time shipping. Your mail order company advertises that it ships 90% of its orders within 3 working days. You select an SRS of 100 of the 5,000 orders received in the past week for an audit. The audit reveals that 86 of these orders were shipped on time. Okay? So what are you claiming, people?
What number is this?
We're claiming that P is 0.9. Correct. 90%. Now, we know that the population size is 5,000. So what would 100 of the 5,000 be? Well, actually, our sample size is 100. Okay? It is 100. And then they also said, let's see here, what else we got? You select an SRS of 100, so you find that 86 of the 100 were actually shipped on time. That's 86%, right? So that means a P hat of 0.86. Yeah. Okay. Question A says, if the company really ships 90% of its orders on time, what's the probability that the proportion of SRS of 100 is as small as the proportion of your sample or smaller? That was really weird. Yeah.
I'm going to need you to repeat that in English.
If 90% is true, what is the probability that the proportion in our SRS of 100 is as small as the proportion in your sample or smaller? And every question is like this. I think you have to figure that out, right?
Yeah.
I think the hard part is interpreting the question. So I think they're saying is, what is the probability that this actually becomes that? Okay, or smaller. So it's what's the probability of getting this or less? Well, you're finding the probability of some z-score being less than or equal to whatever we get. Right? So we just keep doing our z-score. So we're going to go statistic minus a parameter divided by standard deviation of the statistic. So it's going to be, let's get the standard deviation over here. That's going to be the square root of 0.9 times 0.1 divided by 100. So what's my standard deviation here? What's 10% and 9% and then divided by 100?
What's what percent?
0.9 divided by 100, so 0.009.
Yeah.
Is it? Okay, so we're going to divide by 0.009 here. So, find me a z-score, please. So 0.86 minus 0.9. Ah, touche. Touche. 0.03? Thank you. Good looking out. Yeah, 0.03. So what's our z-score then? .33. So if I go over my chart, look for a negative 1.33. 1.3. 0.0918. Yep. So that will happen less than 1% of the time.
How do you know when, so, like, I have a hard time, like, because I know all these processes, but I have a hard time identifying when to use them. So how do I know when to use these things?
Whenever you try to find a probability. That's really what's going to come down to almost all the time. They want you to find a probability of this happening or this not happening. Then if you want to do that, you got to go to the chart. To get the chart, you need to use a z-score, which means, hey, I'm going to have to get a z-score.
So I'm saying that 9% of the time it's going to be
you're gonna get this percentage or less.
Didn't you just say it was 0.1 though?
Yeah, that's about 1%, isn't it, if I round it?
Apologize.
No, because that's 9%. Wouldn't that be 10% of the time?
Touche. 9% of the time.
Yeah, so 9%.
You were correct, I'm not.
Yeah, so 9% of the time.
I'm
you get-
wrong, you were right. Stop Cheeto.
Just like I'm just clearing things out.
Yes, you are clearing them out with your smartness. Thanks for putting me on blast on the recording.
Shut up.
I'm just saying you're right, dude. Good job. Good job.
You're like making me feel stupid in the process.
Payback. No, just kidding. Go ahead.
How come when you're doing the standard deviation of p hat, you lost all that? So it's just standard deviation of p.
Well, you really want to get P. Now, here's the deal. Thank you. Gracias. That's a fantastic comment you just made. When we're trying to find standard deviation of P hat, the formula reads P times Q, doesn't it?
Yeah.
So if I have that, use it. Sometimes it won't give you P. And P hat might be the best estimator you have. So if you have no P, then you're going to use P hat in that case. There's just no other way. So then that means you would be using P hat, Q hat over N. Fantastic. Why do you gotta go all the time, dude?
Really? I'm so mad at you.
Alright, cool. So that was part A. Part B says, it has your name on it.
Read it.
Okay, no, never mind. A critic says, aha, you claim 90%, but in your sample, the on-time percentage is lower than that. So the 90% claim is wrong. Explain in simple language why your probability calculation shows a result of the sample does not refute the 90% claim.
Give me there.
Okay.
Sampling
Where are you going?
variability. Okay? Can this still happen?
Yeah.
Yeah, it happens 10% of the time. About 10% of the time. So maybe you caught us on a bad day this day, or this week, I mean, because there were weeks numbers, right? Caught us on a bad week. But on the next week, maybe you catch us on a good week. But on average,
But whenever asked like why it would be wrong, just say sampling variability.
you could say you would be more detailed. But when I say sampling variability, y'all should understand that this is one sample of the many, which means that this could be on any end of the distribution. So it just turns out that yours maybe was here instead of being somewhere here where it's truly representative. Or maybe, on some other week, it could be up here somewhere, and it says, wow, man, you really actually sent 99% of your packages on time. So it just turns out that we happened to get a low sampling this time.
Wait, isn't it just like whether or not the claim is correct?
When you're doing an SRS, it's kind of like throwing a dart at a dartboard without looking. And you just catch one of them. Like, oh, snap, today I got a good one. Okay? Most of the time you'll be on the board, won't you? But sometimes you hit the wall. And sometimes you'll hit the target. Same idea.
Isn't this just like whether or not this claim is correct? Like what would you expect to see for letter B?
What would you expect to see?
Like wouldn't we just like expect to see like 86%? Because that's what I got.
No, we should really be expecting 90, but because of this sample, this week's scores, it turns out that it was less than 90. But is that truly representative of all packages?
Yes.
Well, if we had no other idea. But if we kept doing this over and over and over, we would find that the true mean happens to be the 90. Because one snapshot is kind of like living in the law of small numbers. Remember we said that?
Yeah.
Where you think, this is what really is, but it's not. What do you need? You need repetition, 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 repetition. Okay? Fantastic. That's 46. Any others? I could store something very small in here. It's just the cover.
You get 45.
Yes.
You get 45. Remember 45?
Yeah. Magazine Sports Illustrated asked a random sample of 750 Division I college students, do you believe performance-enhancing drugs?
Do you believe empty?
Guys, be quiet. We're just trying to have a conversation. Oh, right. Are you done? Because we don't want to be rude and like interrupt this. I already regret it. The magazine Sports Illustrated asked a random sample of 750 Division I college athletes, do you believe performing enhancing drugs are a problem in college sports? Suppose 30% of all Division I athletes think that these drugs are a problem. The P-hat. I'm sorry, I'm just really distracted right now. Let P-hat be the sample proportion who says that these drugs are a problem. You okay there? All right. Okay, so anyways, jumping over to 45, which was the question. The question is... I don't know.
Nothing, Chief. We just made eye contact.
Okay.
No, we're not. I need to go home. Can I go home?
I feel the same way. So the same way right now. So anyways, the question says here, decreasing the sample size from 750 to 700 or 300, wow, to 375 would multiply standard deviation by which of those numbers? What's going to happen here?
Did you repeat that? You talk so fast.
I know, I'm sorry, but here's the question it's saying. They're taking the sample size and they are decreasing it. Like if they were going to find the standard deviation of this bad boy, that's the square root of 0.3 times 0.9, correct? No, that's not 9. 7, thank you. 0.7, and then they're going to divide it by, how many did they sample?
750.
What was the first one, 750? So they're taking the 750, and they're decreasing that, and now it's becoming 0.3, 0.7 over 375, right? They're doing half of that. So the question is, what's really happening when I do that? When I decrease the sample size, it's equivalent to multiplying by something. Look, they told me. They decreased from 750 to 375.
Oh, okay.
They half the sample size. So what would happen here?
Wait, they have.
Well, just do some algebra, people. Here. So, let's see here. How do I get rid of a square root? Square it. So, standard deviation squared is equal to, how much is that number right there? The 0.3 times 0.7. How much? Sorry. Thank you. I'm not present today. So 750. So let's see here. And they're taking this and they're making it smaller, right? So that means that they're multiplying this by 2, correct? Would that do that? Would that decrease the sample size? Because doesn't that cross cancel? Or cross simplify?
Oh, yeah.
Where are they multiplying it by 2 or
Well, how do I get this number to come to be half the size?
Multiply by 2 over 1, right?
Right, I multiply by 2 over 1. So instead of multiplying by 2 over 1 here, I'm going to multiply by a half, isn't it? Correct?
Yeah.
Okay, cool. So that would decrease the sample size here. So here's what I'm looking at. Here's the idea. So I guess it's multiplying by half, which is C. And just double checking that. No, B. Why the square root of 2? Oh, So take it back. Square root of 1 is 1. Square root of 2. Huh. The world may never know. Yeah, so if I square, that standard deviation is. What was this, 0.21? And I want that to be half, so I would multiply by 2, which means multiply by 2 over here. Oh yeah, so multiply by 2, so there it is. So, yeah, that brings it back, so it's a square root of 2. What did I do in the other one? Was it a half?
Multiplied it by half.
My bad. Yeah, whatever I do to one side, I gotta do the other side, don't I? So if I multiply that side by 2, then I gotta multiply that side by 2.
Yeah.
Okay, my bad. Okay? My algebra flying here.
Go down and
Yes. Embarrassing. Other questions?
College boys gonna watch your video. Who is this guy?
I'm never
Like,
gonna
how
watch
is
this
Mr.
video
Movie?
again.
Let's watch it right now. While
I'm gonna go live.
Watch it while recording?
Yeah.
Let's watch ourselves record ourselves.
Is it live?
Reaction to
Yeah.
the reactions.
I want to watch myself while I teach myself.
I thought he had. Okay, I apologize.
Yeah, see, that's recorded now forever. Your apology is forever. I'm gonna take that apology and I'm gonna like loop it over and over and over and over. Man, Savannah's sorry for everything.
Luis's eye immediately regret that.
So if I were to like go over there, would they see me?
No, I turned that camera off. Here, I'll show you what you can see now. That's all you see. If I turned it on, then you would see that. Then I could be like,
Dude, that's weird.
because it has to stream, bro. Did you want to get in there?
No, I don't want to get out.
Inception. Okay. All right, I gotta move on because I gotta get this next part recorded for the other class too. So, actually, let me do this. I'm gonna stop this piece of it.
Oh, I have that.
Notes?
I have those.
Yeah, notes.
After the robbery date, or I have one of those after the rivalry. I like ride my business so it doesn't hurt so bad.
Okay. I always wish I was a tap dancer. I think it's so cool. You know how to tap dance? One thing you know how, you don't ever forget it, right? Yeah. It looks like you just, I don't know. It looks like it's so fun. And like they're like hopping around. And like, okay. I need to get a haircut. My hair's falling or something. Is it falling again? Do I need it? Stay. Estate. Alright, so 7.2, Janessa, was on sampling for proportions. So the sampling distribution of proportions. There's another type of data, which is means. So what we're going to do in the last section here is a sampling distribution for means. So the distribution of sample means. So the question is, how do we work with sample means when we're trying to work with a normal distribution? Well, the beautiful thing here is that these are in the same type of category, isn't there? So, get these formulas down first. These are your two formulas you're going to want to use for wanting to use your normal tools with a distribution of sample means. And they should also be on your formula sheets. Now again, looking at the very first formula, if x bar is what you have, then that is your best estimator for the parameter. And that's what you'll use. Okay? Moving on. Okay. So, oh, sorry, Priscilla. It's not like they're written in Greek or anything. I thought that was. I thought it was for a minute. Sorry. All right, cool. Can I move on? All right, cool. So, here's the thing. Two scenarios that I can present you with. If you're looking at distribution of sampling, sorry, if you're looking at that. If your sampling distribution came from a distribution that was already normal to begin with, would you expect anything different from the sampling distribution? So if the population distribution is normal, would you expect the sampling distribution to be anything other than normal?
No.
No, good. So there's the first thing that you need to know. If you sample from a population that's already normal, then the resulting distribution of sample means is also normal. Now the only way you would know that is if they told you the population is normal, therefore the sampling should be normal. Now they won't tell you that the sampling will be normal. They'll say, hey, based off of this normal distribution, we found these statistics. Then right there you can say, hey, that means my sampling distribution must also be normal. Okay, they're not going to give you the rest of that rule. They'll just give you what you need. Okay? So, if the population is normal, then the sampling will be normal as well. I'm just going to continue with this slide. It's all good. If the population distribution happens to be mu comma sigma, normal, then the sampling distribution is going to follow these statistics. So this is what this is saying is, oh man. Sorry guys, I'm going to have to put the, let me, smart view transparency, so you can see and I can write, and it will be beautiful. Sha. What? Okay, so here you go. Okay, so here's what they're saying. If the population is normal, then your sampling will be normal. And again, this is normal notation here. If your distribution is normal, then your sampling will follow this distribution. That means that the mean will be the mean mu. However, your standard deviation will become sigma over the square root of n. Sorry for my notation. It is equivalent algebraically, but it's simply sigma over the square root of n. That will be your new standard deviation. You understand? So, mu comma sigma over the square root of n. I think that's the way they give it to you in the formula, on the formula sheet. So use that. Okay. Questions?
Oh my God.
All right, cool. Moving on then.
Wait, no.
Okay, I can know.
That don't feel great.
Wait, are these on it?
I don't see it.
Yeah, they're on the back. On 3. Right under statistic and there's a little box. Yeah, that one right there. They're in a little box.
Oh.
You see them, the first two?
Yeah, I see it. I thought it was the first page.
It's both of them, huh? One is the mean, the other bottom one is the proportion one.
Yeah.
Okay, still mean for proportions. So, this is how you satisfy. Remember how there was those 3 rules for distributions? We have to, we have to check for bias, we have to check for normality, we have to check for independence. So, for starters, bias, what's the only way you can answer that bad boy? Is SRS. Here's your answer for normality. Okay, if the distribution is normal, then my sampling will be normal. Okay? And here is the kind of rule we can check that as well here. For, what is it? Independence. It's the same rule. 10 times sample size. If the population is at least 10 times sample size, then you say, yeah, this is independent. Okay, so bias, we already know. They told us normality. If the population is already normal, then we're good. And if we want to check for independence, then 10 times the sample size. Everyone cool with that? Here's the next thing, though. This is ideal. This is saying if the distribution is already normal, then your sampling distribution should be normal, right? The next question is, well, what if your population isn't normal? What do you do then? Right? Here's what comes in to help you. This is your lifesaver. This next idea is called the central limit theorem. The central limit theorem. And the central limit theorem says, if you draw any SRS from, or sample size n from any population whatsoever, skewed, uniform, bimodal, a distribution whatsoever with a mean mu and a finite standard deviation, when n is large enough, then the sampling distribution of sample means will be very close to the normal distribution of that.
What does that mean?
Oh, it's saying that. Remember how I told you if
No,
it.
not these, but this.
What does it all mean?
Yeah.
I know. And I think I already said it a couple times. If my population is funky, bimodal, excuse, is there a question?
Yeah, can you make this so then I can put it in my notes because I really don't want
You don't know what?
I don't want to write all of that.
No, you don't have to write all that.
Way to stay-
Here's the simplest way to say this. I have a funky population, right? It could be skewed. It could be super skewed. It can be, okay, it could be the weirdest, ugliest thing that you could ever think about. Okay? That's why it's saying any population whatsoever. Okay? As long as n, and what is n, people?
Population.
Sample size. As long as your sample size is large enough, then that means that the distribution of sample means will be approximately normal. Simply said, one more time. As long as your sample size is large enough from any distribution whatsoever, as long as n is large enough, then your sampling distribution will be approximately normal.
Yeah.
How do I know that it's large enough? I think I gave you a rule on that one already.
Oh,
the normality?
No, that's for parameters. That's right, that's for proportions. That rule does not apply here. Okay? 10 and 10 is not central limit theorem. Okay? That's for proportions. I need to have at least 10 successes, and I need to have at least 10 failures. For sample means, I can't use that because that's strictly a proportion thing, isn't it? Here I'm working with quantitative data. So, central limit theorem, and I think we talked about it. As long as my sample is large enough, and I gave you a magic number.
Oh.
Yeah, that's the one right there. As long as my sample size is large enough. Now here's the deal, guys. Read any book, they won't tell you. All they'll say is, if the sample size is large enough. Okay? Now, I want to show you some stuff before I move on. Okay? Here's some pictures. Here's what the distribution started off as. It looked like this. That is ridiculous, right? That is no way normal, or even near to be normal. If I did a sampling distribution where sample size was 2, it looks like this. That's skewed. But it has some, it's getting better, right? If I go to 10, it looks like this.
It's still a little skewed, but not.
It's still a little skewed, but not as skewed, right? Take a look at sample size 25.
It's almost
Nice.
This is almost perfect. That is approximately normal. Okay? So when they talk about central limit theorem, and if your sample size is large enough, then you want to think about that sample size being at least 25. So you're going to say as long as the sample population, your sample is greater than or equal to 25, then you can say that the distribution is
Approximately.
mu comma sigma over root n. It's approximately normal.
I can't just say normal. I have to,
No, you never say no. Even when it was population data,
can we say
we
approximately?
never say normal. We always say
Approximately.
approximately normal. The data looks approximately normal. So, here's the deal, guys. Let me see if I have a blank slide up here. Oh, were you guys done with this one?
Yeah.
Okay, cool. So let's take a look at this slide. Here's an example. The time that a technician requires to perform preventative maintenance on an air conditioning unit is governed by the exponential distribution. Exponential distribution? What? Whose density curve has a mean of 1 hour and a standard deviation of 1 hour. Your company operates 70 of these units. What is the probability that their average maintenance exceeds 50 minutes? So, everybody realize what that distribution looks like?
My cat's about to die.
Your what?
My cat. I'm not sure if I died of purple or because he's eating his litter. It's for science.
Moving on. So, here's what we know from the last guy. His distribution, what's it look like? Exponential. So, it probably looks like this somehow. Just like that example I showed you was all ridiculous, okay? So, here's the question. Can we really use our tools with this? Well, let's take a look. Are the restrictions on sampling fulfilled? Sampling size of 70 is less than 1/10 or 10 times. Do you think that heat servers more than 700 ACs? Definitely, right? So that's 10 times the sample size. So it looks like we've met that one. That's the independence rule. Was there a bias here? It really didn't say, did it? Let's take a look at the next part. The population distribution is not normal, but the sample of 70 is large enough that we can call in which feature now? The central limit theorem to help us out and say, hey, looks like it could be normal here because 70 is definitely not large enough to do a normal distribution. So then we can say that, and then we have that deviation there. So it would be very close. Okay, 1 over square root of 70. So we get that 0.11195. We're going to do our z-score from that. Notice how this changes from the last one, doesn't it? Okay, last time, yeah, so this time now we have x and we have the x bar. Technically it's really going to be x bar and the population parameter, but it's the same idea always, okay? It's a statistic minus the parameter divided by the standard deviation of that statistic.
Oh, it's right there.
That's gross.
Gross.
Should have done it yellow.
Why? We don't let him pee himself all the time.
Pikachu.
I was gonna do that. But you dyed your cat? Yeah.
Why'd you kill him? That's horrible.
He's purple. Oh my
Okay,
God.
so here we go again. So here's the math behind it. Thank you for putting your phone away, Janessa, before it becomes part of my pocket.
But my mom's gonna tell me my cat's
1,
gonna
2,
live
3,
or not.
4,
My cat.
5, and there we go. Okay, so there's our probability. Wow. Yes. What would you say? If it was biased, what would you say? 3 letters.
PWC.
PWC, what does that mean?
Proceed with caution.
Proceed with caution. Okay.
Correct yourself before you wreck yourself.
Oh. Okay, here we go.
POW.
POW, prisoner of war.
That's me.
Okay, take a picture, guys, because I'm going to get rid of that. I was going to say something
Hey,
else.
can you get me one, please?
I'm not getting a book.